want to welcome you to this month's Quantum Marketplace. This is a series of webinars, and I'll be turning it over shortly to Mark Wippich, who's going to be moderating today's set of presentations. But this is really part of what QED-C is about. That is sharing information about QED-C members, helping them reach a broader community of customers and suppliers and partners. So please give us feedback. We're always interested in knowing how QED-C can further help the membership and grow and enable the quantum industry. So with that, I will turn it over to Mark Wippich to kick off today's program. Over to you, Mark.
Great, thank you, Celia. So let's just get right into it. Got a little bit of a late start here. So we're gonna have 5 presenters in the area of quantum entanglement. So I'm gonna highlight over that. And we're gonna go into some market dynamics, and then we're gonna move to a roundtable panel discussion. And if there's time permitting, we'll show the future webinar schedule that's tentative laid out. So quantum entanglement, what we're doing a little differently this time in the quantum marketplace is we're gonna have 3 companies presenting that are part of QED-C that are all on the source side, and in some cases making more products than just sources for entanglement. And then we're also going to have 2 users, that actually use this type of product now or in the future. So Noel Goddard from Qunnect, you're first. Why don't you take over and start presenting?
I need the ability to share screen.
Mary?
Got it. Okay. Projecting okay?
Not yet. Yep.
Now we can see. Okay, great. So my name is Noel Goddard. I am the CEO of Qunnect, and I have been charged not only to tell you about what we're doing with entanglement sources, but to give a small overview of entanglement sources and where the field / commercial realizations are. So I'm happy to be with you here today. And as you might all know, it all starts with the source. Basically, we all know that we can't do anything in any one of the 4 major pillars of quantum tech, which are computing, networking, sensing, and imaging, without having high quality qubits. And that starts off with being able to have high quality entanglement. So there are many desirable features in entanglement sources, and I'll speak to a little bit of these in each one of the examples. But first, it would be great if they were on demand. Then universally, having high brightness, having high fidelity are very important. And some things which I'll speak to in some of the latter slides that are coming to light is compatible line width. And largely that's because what I've highlighted down there, device interface losses are really key as we start going away from having single quantum instrument type experiments and now talking about quantum networks, larger quantum devices like computers who are trying to interface to those networks. And then also, I think on the wish list, of course, is that these sources are directional, that you have coherent emission, and that you have good heralding efficiencies. So qubits come in many flavors, hence entanglement also is in many flavors. Entanglement is sort of the extension of the concept of superposition to multi-particle systems. On the top, I've shown 2 examples that you see a lot in the optical community: polarization entanglement and time-bend entanglement, which leads to polarization qubits and time-bend qubits. And I've shown them in an example of block spheres, which we've become rather used to in the quantum community, for being able to describe any combination of all the possible combinations you can have across the entire sphere worth of space. And at the surface of the sphere, you have entanglement, which actually is highly coherent. And that's really the key to being able to assure good quality quantum operations, is to assure that we're actually in those highly coherent states. Just below those optical ones, I've mentioned the OEM qubits and spin qubits, but there's also ionic qubits, charged qubits, flux qubits. I mean, they come in all different types of flavors and all need to be high quality. So the first type of source, which you'll hear some about today, I assume, are these deterministic sources. Those are not yet commercial, largely as a function of the fact that they're extremely hard to manufacture. The most common example that we know of right now are quantum dots, which are embedded in either nanostructures or films. I've shown a few examples here. These are parabolic wells, these are nanowires, and these are a film example. And what's nice about deterministic sources is that they're on demand. And that's, of course, useful for being able to use them in technological sort of experiments and applications. Also, something that's very interesting is that they're capable of having high brightness also with a high degree of entanglement, because the pair generation rate is decoupled from the G2. And all of that's useful to us in terms of thinking about how sources should be in the future. But as I said before, this is something that's been very hard to actually realize industrially. They also have narrow line widths, good fidelity. And I think one of the very interesting things which has come out of this community is that they're very tunable through being able to induce strain on any of those nanostructures. The more common one, which you see and you're going to definitely hear about from some of the providers today, are these non-deterministic sources that really come in two flavors. One is a spontaneous parametric down conversion called Sbdc, and the other one is spontaneous four-wave mixing called SFWM. And both of those are arguably tunable because they're two types of effects which use some type of pump lasers, which you see here on the left, in order to pump to an excited state. And depending on which one of these two that you're following, you decay from that excited state by giving off photons of either equal energy or differing energy levels. And depending on what you've actually picked as your pump lasers and the atomic levels which you're exciting, they're arguably tunable sources. For the Sbdc sources, which we're seeing now on the market, one compromise is that they have rather large line widths. And we've found a number of suppliers now that are starting to narrow those with cavities. You're certainly seeing in a lot of academic papers. For the four-wave mixing type sources, the line widths are narrower by definition. However, the generation rates are a little lower than what you can get in the Sbdc sources. So unfortunately, on the features list, they're not on demand because they're not deterministic. And you also have this problem that the harder that you pump them, right, you start to compromise the degree of entanglement. So they're not as good as quantum dot sources in that extent, but we do now see sources that have high fidelities. Again, the line widths are sort of all over the map depending on how you're generating the photons, but they are wavelength tunable and directional. And again, on the commercial supplier thing, this is by no means a full list, it's just a partial list, but you'll notice a lot of suppliers of Sbdc, including Qubitekk, that we'll speak later. Qunnect is in the category of the four-wave mixing. So just to give you an idea of Sbdc Applications, this was one of the two papers that were highlighted in the cover of Nature in early June, coming out of the Barcelona group of de Reed Martin. And in this paper, they had two separate Sbdc sources that were cavity narrowed in order to couple to two quantum memories, which they entangled at telecom frequencies. In order to make this experiment work with the very high effective fidelities that they reported of 92%, they actually needed to narrow the line width of their sources to 1.8 megahertz. And just starts to give you an idea of the challenges which are out there whenever you're trying to couple quantum instruments to quantum systems. That's exactly why Qunnect is doing what we are doing in terms of building our own atomic source, which is based on four-wave mixing. Again, we need narrow line widths. In our case, we're using atomic vapor memories that I'm going to describe in the next slide, so they're also natively compatible. And we've decided to build all of our instruments in these sort of standard drawer racks, which we're rather proud of because now we're looking towards building quantum systems. In our case, what we're very interested in is producing photons both at telecom wavelengths and at the wavelengths which are optimal for our memories. So stay tuned. And that's because it's part of our larger repeater product suite. We not only create entanglement sources, which are actively in development in our R&D labs, but we also create quantum memories. And with those two, you can start to actually host entanglement swapping protocols like I've shown here with the multi-node system, which are the basis of quantum repeating. And our flagship product at Qunnect right now is another part of that suite called a quantum memory. In our case, it's an on-demand EIT, which stands for electromagnetically induced transparency memories. This is a CAD rendering of the actual device, and we're very proud to announce that we will be shipping our first beta prototype units with the specs that you see below in September, with the hope to start producing our Mark 1 units that would be broadly commercializable in early 2022. And as I mentioned in the Sbdc slide from the Barcelona group, source requirements whenever you start to try to couple sources to memories or sources to any other quantum devices are really important. In our case, we have very narrow line widths that are demanded by EIT, and also wavelength specificity because we have specific wavelengths in which our memories function best. So this is one of the reasons at Qunnect that we spend time developing sources, because I want our sources to be highly efficient with our memories. So if you'd like to learn more, please go to qnect.inc. And if you happen to be passing through New York, we are located in the Brooklyn Navy Yard, just across from Manhattan. We'd love to show you what we're up to. And thanks so much for the opportunity to speak today.
Great, thanks, Noel. So Mike from Thor, are you online?
Yes, I am.
Okay, great. You want to share your screen?
Yes. Should be popping up. Let me know when you can see that.
Yep, I can. Can you put it in presentation mode? There you go. Thank you. Go ahead.
Okay. So I'm Mike DeArmond. I'm here representing Thorlabs laser division. If you're not familiar with Thorlabs, we've been in the photonics community now for 30 plus years. We're a vertically integrated company. So we do everything from optical mirrors, filters, to fiber draws, including some technological abilities to do even some soft glass optical fibers, mechanical assemblies, machine work, et cetera, all the way up to the full systems. Since our inception, we've now grown to represent more than 2,400 employees worldwide, and that is over 25 locations globally. Those 25 locations you can see here represented by the pins in the map. You'll notice in North America, there is a few black pins, and those represent laser division, which is what I'm part of. And it's one of our products that I'll be introducing you to today. I'm based here in the headquarters in New Jersey, which is also where we produce our source, which Noel has already discussed. The general type, which is an Sbdc type source. Now, this is not so this is a little bit different for this venue. It's not an entangled source. It is a heralded single photon source. So we're really targeting single photon work. And our goal here was to produce a low barrier of entry to customers to get up and running quickly to do single photon work. In order to do that, we're using a type 2 collinear Sbdc source, and we take those two photons. So we have an integrated 405 pump laser to produce degenerate pairs at 810. And then we split those two polarizations off and we fiber couple them to outputs to the signal and idler channel. And you can see those here on the right. That includes the patch cables as well. And it's a high brightness source. So many hundreds of thousands, 450,000 pairs per second on a high heralding ratio of about 0.45. Again, the goal here was to really provide something turnkey that somebody can quickly get up and running and start operating. So it includes everything you see here on the right, the power supply, the communications link, and also even the fiber patch cables, just to make sure that you're really able to use it quickly. And if you don't want to mess with your own control software and use the available serial commands, you could instead use a GUI that we provide for the users as well. And then in line with sort of other Thorlabs products and our company in general, this is a product that we try to keep stocked. So it's something that you could literally go on the web, put in your cart, add it to your cart and have it shipped in a couple of days and be ready to get up and running. As I mentioned, this is the first type this type of product for us, for Thorlabs and for laser division as well. And it's going to serve as sort of the building block for the next generation of sources, some of which Noel has pointed out are of interest. And some of those you can kind of guess what they might be. First and foremost are other wavelengths. If people are interested in 1550, the telecom wavelengths on top of the 810. Other things in our short-term roadmap are narrower line widths. We've heard that, and we know that is a hard cutoff for barrier of entry for some application spaces. And then of course, a truly polarization entangled source. It'll follow the same ethos and design principle of being simple to use, fully contained, and delivered quickly. And then there's more to come. And then, to earlier points in terms of connecting people, what I really hope to get out of this is also some feedback that I've already gotten a fair bit of, and that is, what is the market demanding? What would they like to see? What barriers do you see in your application space? Thorlabs offers more than 20,000 products, and about 20% of those are either customer inspired or directly requested by customers. So I'm really kind of hoping to get some feedback of where you'd like to see us push these sources. And coming from not only Thorlabs, but also the laser division, we're a pretty small and dynamic group. And so our runway from product conception and market demand to a released product is relatively short. Makes us a great potential partner for anyone looking to develop a solution for your application. So with that, I'll leave you with my contact there. Feel free to reach out. I see some people in the room that I've already corresponded with. So yeah, feel free to reach out with any questions. And I guess with that, I'll also take questions now if there's a little bit of time, Mark.
Great. Thank you, Mike. Actually, I have a question for Noel as well, but we're trying to make up a little bit of time here, so we're going to cut some of this short. But I do have one key question for you right now. Wow, that's impressive. I mean, you're actually selling from inventory. That's pretty wild. In quantum, that's pretty wild, in my opinion, right? So what, in terms of what do you see as the best markets, or what is Thorlabs looking for this particular product? And we realize you're going to have a polarization entangled source upcoming pretty soon. Where do you think these products are going to be the most useful for customers? What applications?
Yeah, in the short term, if you just want to talk about this type of heralded source, we're primarily seeing things for any sort of single photon work. I know that's sort of redundant to say, but a lot of sensor testing, basic communication and encryption protocols. It's really something designed to put on your benchtop and quickly workshop an idea, right? To quickly get up and running and test some things in principle, do it inexpensively, do it easily with a warranty and support and everything else. And then moving on to those entangled sources, obviously it's an entirely different application space. There are a number of applications that you can't really access until you have that polarization entangled source. So that's sort of looking ahead, and then we're excited to move into that space as well.
And also a 1550 version, which is also critical.
Yeah,
right?
Absolutely. And that is, I hate to tell the engineers how easy their job is, but it's a relatively straightforward swap. Once you have this platform to swap out a pump laser, a crystal, and some related optics. So it really does make it pretty relatively straightforward to deliver those other wavelengths or custom wavelengths, and not custom, but maybe shifted wavelengths, I think is probably a better term. Yeah.
Great. And then, so in terms of, this is a pretty powerful statement you have on your takeaway point here in the slide, so you want customers to reach out to you, even if they have a custom requirement in this particular area?
Yeah, that's right. We want to see that feedback, and there are some, it always makes, that's always sort of been a guiding principle of Thorlabs, right? To be customer driven, the voice of the customer. We very much focused on that in customer support and service. So yeah, when we see a market demand from an integrator or somebody that feels very strongly about a direction for a research program or an application space to market, it's absolutely something we want to hear about and have an open discussion about to see if we can develop a solution.
Mike, this is Hunter. I think my microphone's finally working.
Oh yeah, I can hear you.
Yep, interesting presentation. So I wondered if you happen to have any sort of a basic comparison spec sheet and or any white papers available, because I'm curious what the power demands are and what the installation looks like in something like this.
Yeah, so the installation, it's quite literally a benchtop unit that you can, yeah, you can put it on your desk, plug it into the wall, and turn it on with the GUI, and you'll start getting photons. We have full specs. I didn't want to cram too much into these slides. You can see the detailed spec sheet on the web. I'm also happy if you want to touch base offline, and if there's something in particular that you want to know about, I'm happy to share those details as well.
Most importantly is likely the power consideration, and also what rack space it might require, and any types of limitations on distance, proximity to other devices, etc. Those types of things would be something that would be considered by the team.
Yeah, so the pump laser has a maximum operating output power of about 150 milliwatts to give you an idea there. So a CW 150 milliwatts, it's a pretty modest power demand. This is passively cooled. We don't even have a fan. It's not really required. So I wouldn't have any grade concerns with proximity to other pieces of equipment or crowding it for overheating. And you can kind of get a sense of the scale here with the optical table with the 1-inch spaced holes, but it's about it's a yay big if you can actually see that on the screen.
That's like a deck of cards. How do that
Yeah.
hand motion again?
It's a little bigger than a deck of cards, about 8 inches by maybe 6 inches or so, and then just a couple of maybe 2.5 or 3 inches tall.
Bigger than a bread box, smaller than the Empire State Building. I get it.
Hey, thank you. We have to move on to the next speaker. So Kay, can you present your slides? Thanks a lot, Mike.
Yeah.
Thank you, Mark. And am I presenting now?
It's coming. Great, I can see it.
Awesome.
Great, go ahead.
Good morning. So my name is Kay. I'm VP of Engineering at Qubitekk, and I'll be talking today about the commercially available quantum entangled sources that Qubitekk offers, as well as our roadmap for sources over the next 3 years. Qubitekk is focused on quantum entangled based devices. We're based in Southern California, and we're growing rapidly. We're hiring engineers and quantum optics experimentalists. Qubitekk believes that entanglement-based devices pave the way to a quantum internet, where quantum computers can intercommunicate through entanglement. That rosy future is based on foundational work that Qubitekk is performing today using entanglement-based networks and communications in various test beds with a variety of partners. Qubitekk builds entangled photon sources in a variety of wavelengths. These have matured over the past 5 years and are stable commercial products that can be purchased today with lead times in the order of weeks. Just call us to talk over your requirements. To answer a few of Hunter's questions, these are about the same size as the Thorlabs device, maybe a little larger. They draw about 3 amps at 5 volts. They're room temperature stable, and you just plug it in and it just starts outputting photons. Our entangled source future is extremely bright. We have a rich roadmap of devices that will be useful for daylight quantum links, quantum memories, launch capable and fully network configurable with data monitoring capabilities. We even plan to offer NIST traceable sources. This is our source on a shaker table, doing some launch practice. I trust I've been able to cast a little light onto the quantum entangled sources that Qubitekk offers, and I encourage you to reach out to us with any needs that you have. We are interested in working with you.
Great, thanks, Kay. Yeah, thanks, Kay. So Kay, so Qubitekk has been shipping entanglement source products for some time now, right?
Correct, yes.
And so what applications do you see most of your products going into today?
So a lot of our customers today are still the universities and large defense contractors. They're all essentially, I would say, kicking the tires, looking to see how they can integrate entangled photon sources into their projects and their proposals. We've obviously got a strong bias towards QKD and entangled QKD supported by entanglement.
Okay, great. And your background is you're not a physicist, you're actually a network ace, right? So it's great to see that you're already thinking about netconf yang and all of that. Care to comment on that?
I think what we're seeing is as you try to network devices and you try to interconnect computers, we're building the internet of the quantum internet, let's say. And so if you roll back to the 60s and how the original internet was incarnated, people had to start thinking about how to connect these islands of computers. And really that's one of our strong focuses, is how do we connect these islands of computers and build that quantum internet. And really, some of the work that we do with entanglement distribution across large scale fiber, long range fiber, is foundational to that effort. And we see that the quantum internet will be based on quantum entanglement.
Great, thank you. Okay, let's move to Chris Monroe. Chris, you ready?
Yes, I am. Let me.
All right,
Here.
share your screen.
Okay. Thank you, Mark, and also Scott Davis from Veston for having me here. Always a pleasure to meet with QED-C folks. So I'm not sure I'm a user or a provider of entanglement. I guess representing IonQ, or a little bit of both. And I want to tell you what I mean by that, and also concentrate on the optical nature of the quantum computers we're building at IonQ. So this here is a picture of exactly 80 ytterbium ions, individual atoms. They're glowing because we're shining laser light on them, of course, and collecting their fluorescence. They're trapped on a, they're levitated on the chip below there, which was made by Sandia National Labs. They have a very big ion trap and quantum information group. And we use these chips. We've built our own as well. They're in a vacuum chamber, and I don't want to talk too much about quantum computing, except to note that our eyes and ears on these qubits are classical optical sources, lasers, modulators, and so forth. And we have individual laser beams that are poking on these atoms. And so in a sense, we're generating entanglement by moving the atoms. They feel each other. I won't get into the details there, but the important point is that this is all of the optics is classical. There's nothing quantum about that. The entirety of the quantumness is are in the atoms themselves. They are perfectly replicable because they're each atomic clocks of the same element, same isotope. So we don't worry about manufacturing qubits. They are already manufactured and they're perfect, meaning they have no idle errors. When you leave them alone, they last as long as you want because they're atomic clocks. Of course, our decoherence is limited by reducing by the noise of the classical sources, and that's really the issue at hand. IonQ is a startup that formed a few years ago. Jungsang Kim and I co-founded this in 2015. Jungsang Kim at Duke and me from the University of Maryland. And again, we make quantum computers, but I would say we don't really build anything. We just integrate things. We buy stuff from like Thorlabs, from like Harris, and we use Sandia chips. This is an example of one of our own chips actually made out of quartz. And we're notably going to become a public company very soon. So we'll have a bank account to be able to explore in many different directions on the scale up issue. So it's easy to add atoms. That's not the problem, especially because they're identical. So unlike any other platform, we don't worry about manufacturing inhomogeneities as we scale up. The scale up is hampered by a control issue. If you look at our technology 5 years ago, here's a university lab. That doesn't look like a computer. It certainly doesn't look like it scales. But in fact, like all optical systems, if you know what you're doing, you freeze it and you manufacture it. And because it gets smaller, it actually performs better. So we're well on our way to making very small ion trap chambers and quantum computer modules. This is from Jungsang Kim's lab at Duke in a collaboration with Cold Quanta, also an active QED-C member, where they've actually made the vacuum seal right on the chip itself, the standard chip for holding these. We're working vigorously at IonQ to integrate optics on the chips, the classical optics, but I want to talk for the last 30 seconds or so on this vision, scaling up our quantum computer in a modular fashion by making optical interconnects between chips. We feel strongly that any scalable quantum computer is going to have to be modular. That's a very hard statement to prove, but I think our experience is anything that's complex, like airline routes or classical CPUs, they have to be modular to scale. We don't see football field sizes of Pentium chips, for instance. So fortunately, with these trapped ion qubits, they're all identical. They produce single photons. They're optically active, and these single photons are exactly the same wavelength, exactly the same bandwidth, so we don't worry about mismatches. They don't exist with these atoms. We do worry about speed and the speed at which we can link two quantum processing units, say rack-mounted individual chips here, is limited by the heralding rate. It's asynchronous, but with memory, with extra qubits, we can make it synchronous and a little faster. And Mark recognized this optical switch. It's going to be a central nervous system of a modular architecture to scale. And I guess the big picture here is, well, there's a picture of Jungsang Kim standing next to the biggest optical switch ever built that he had a big part in at Bell Labs about 20 years ago. But I guess the take-home point here is that there are no wires between these qubits. It's all optical, either classical or these photons. Everything is controlled by software. The configuration of the optical switch tells you what your network graph looks like. The entanglement within qubits in a single QPU is all in software. So this is a totally reconfigurable system to do error correction on the fly, to be tailored to any algorithm you want. So there's a lot to be gained in the upper levels of the software stack in this particular hardware. And my last slide is a little bit of a catch-all, but I show this one a lot. I think quantum computing is the hardest and probably most important quantum application that has the most promise in a sense. But a quantum simulator is just a specific purpose quantum computer, so there are going to be great overlaps there. But one thing that's maybe not appreciated is that quantum computing and quantum communication are exactly the same thing to scale. If you build a big quantum computer, you are making a quantum computer network. I think some of the previous speakers here have accented that as well. You have to make it modularly, and optical photons are probably the way to do it. Conversely, if you're going to make a large-scale quantum communication system, you're going to need quantum repeaters, which are nothing more than small quantum computers. So having the protocols to interface matter qubits, memory, with photons, it was really done first with atomic ions, maybe 15 years ago. And I think the protocols will be developed in this platform to make big computers. And eventually, when we get to telecom wavelengths, maybe we can go large distances. Quantum sensing, of course, is related to all of these things, but maybe in a little bit different way. I think distributed sensors will be entangled to beat the shot noise limit. They may involve interesting entangled states that may be produced by a quantum simulator or a quantum computer. So with that, I guess we make entanglement and we use it, and we buy everything from QED-C members to make these big systems. Thanks.
Great. Thanks, Chris. So you sort of answered a couple of questions I was going to ask you. So I just, if you can give a 30-second blurb on, so are you saying that quantum computers, when they actually become reality, assuming they become reality and useful and pass quantum supremacy and they're used every day, are they going to require entanglement to be connected together to scale, in your opinion?
Yeah, I guess it is my opinion. In principle, you can do it with one big chip, but the problem with quantum systems, this is another non-theory, is that as you make a quantum system bigger and bigger, it becomes less and less quantum. So I think this is, of course, what we experience in everyday life, any complex system. You have to sort of stop, and you do limit connectivity to a certain extent when you do that, but at least you can grow the system. So indeed, quantum computers will get useful when we have hundreds of adept qubits, and that means qubits that have error rates less than 1/10%, 100%, and that probably means error correction. It means a lot more qubits. It means you have to network them to keep error rates low. So yes, I guess the short answer is yes.
Okay, great. Thanks.
Hi, Chris. I have a quick question. So to scale this ytterbium computer, would you need this routing hardware and the memory at 369 nanometer?
Oh, ytterbium, yes. 369 nanometers is sort of the working wavelength. There are other ions, calcium's in the blue, barium is in the green. So there's a nice, this is very technical, but ytterbium has a very clean atomic structure. It makes it very easy to use. These other ions, it's a little less clean, but not exactly. There's, for instance, a radioactive isotope of barium that is as good as ytterbium, but it's visible. Of course, they're radioactive. Good news is we don't need that many atoms. So I think in the future, we're going to move away from the UV. Thank you for the question. I hate the UV. I've been using it all my life. I think going into the barium system in particular, we're going to be able to use green optics. Telecom's another thing. I think we're going to have to wait for technology, maybe single photon wavelength conversion to be able to hit telecom wavelengths. But good point.
Great.
We need to go visible.
Thank you. Thank you.
Thank
We need
you.
roll to Steve. Steve, you ready?
Okay, let me see if I can share this.
Sorry.
Says I cannot share while another, oh, there we go. Try again. So first of all, well, let me put this in presentation mode. Let me back up here so you aren't distracted. I really like what Chris was saying. I've always thought that computing and network communications are two sides of the same coin. And that was, I definitely agree with that. But to move on here, I was asked to think about more of the pool side of things, like what is QED-C, where we're going with quantum technologies. And so I've broken it down, as most people do, into computing, networking, and sensing. Some computing things, we can envision some applications for power systems, aviation, medical. Power systems would be things like turbulence. I mean, looking at hard problems, which unfortunately we don't see quantum computing being there today, or even in probably, unfortunately, in the near future, but we're monitoring for advantage. When and where is that advantage going to occur? And it may require that network scaling up. And that's precisely where we, or at least I, focus my effort, is on the networking side. And that's where we see the near-term applications as well. I mean, a lot of people know QKD, controversial topic, but it's a commercial quantum product here, and it works, and it offers an advantage in certain aspects of security. And so it's an immediate commercial use case. So we see that as a pool. And I would imagine a lot of people are buying these products to build and improve upon those types of systems. Network time synchronization is big for us, especially for things like time-sensitive networking. And so we really want to explore the benefits of networks, build networks, and maybe they can become the data bus for computing, as Chris was mentioning earlier, or it may help with quantum network sensing. But then when we go down to network sensing, in my view, there's a pretty big blur there. I think quantum technology has always been used in sensing, whether it's quantum noise or being leveraged in more sophisticated ways, but there's nothing new there in terms of quantum per se. But we could see it again in power systems, aviation, and maybe medical imaging detection improvements. So that's where we could see some of the pull, I think, in the nearer term being in the networking area. So what do we want to do with this? Or, again, we want to build, like everybody else, quantum networks to distribute entanglement. And I think a lot of people will say, well, why are you building the network if it can't connect to anything and you don't know what you're going to do with it, other than QKD and security? And I know other people would say, well, just build it, maybe they'll come. But, we oftentimes have to have a better business plan than that. But if we don't have that business plan, or that really clear idea of what people are going to do, at least make things interoperable, make things flexible, highly interoperable, and follow standards, so that in your quantum marketplace, we can easily pick and choose products, make them modular, have them communicate with each other easily. And IEEE P1913 is attempting to start to do that with the NetConf Yang, as Kay mentioned. So it could be, people can build these quantum campuses and do these very quick software-defined experiments for things. And then again, if we want to look back at the pool side of things, where would it be used? Maybe imaging and other sensing applications. But again, only if quantum advantage is ever really discovered there for that. So I have my contact information and.
Great, thank you, Steve. One quick question, and then let's move to the panel. So Are you saying then, in your opinion, that QKD has exceeded quantum supremacy, or at least has made it? Are you saying that, in your opinion?
I would say that we've learned a lot about the pitfalls of quantum technology and its utilization by going through that tortuous product development.
Yeah.
So I always hesitate to use the word advantage, but in my opinion, that, or somebody may say quantum sensing is further along, but I would say networking in terms of the QKD is probably most mature today. Yes.
Great. Thank you. Okay, so let's move on. Thank you, all the speakers. I just want to touch on one thing that was mentioned a bit already, and we've been talking with the speakers about this concept, but there is really a push versus pull. A lot of the source providers or component makers are always looking for more information, and many times they're sort of pushing their technology into the marketplace, but that comes with a lot of risk, right? In fact, it can come with very high risk, right? And so what we're now migrating to in the quantum marketplace is when it's appropriate, is we're working to invite users. So thank you, Chris and Steve, for joining and giving your perspective. I sort of liken this to a push versus pull, and I like to use the concept of a black swan, because sometimes we don't know where this is all going to go. But as we work through this, the closer users and providers can work together, I think we can get to the better answers with less risk. So moving to a panel discussion, I first want to come back to Noel. Noel, you actually, wow, you presented that you're actually shipping, you're selling and shipping quantum memory. I'm not aware of anyone in the United States that's doing that yet. I could be corrected, but can you care to comment on that?
Thanks. That's a really exciting moment for our company. So yes, we are shipping. It's the beta prototype, but we're incredibly proud of it. As Chris Monroe was mentioning in his talk, I think one of the things that we all understand is that the key to connecting quantum processors are versions of quantum networks. And of course, the goal of those being, at least in longer distances, to actually do quantum repeating. And what we're doing is building out the core units for a quantum repeater product suite. And the two things are memories and sources when you start talking about quantum instruments. So yeah, we're very proud. I think, so to our knowledge, we're actually the first memory suppliers globally. So exciting times.
Right, and you're actually saying that you're going to have, so you have your beta shipping next month, but you're actually going to be, you think, almost to or at TRL level 3 in December with the same product, right?
Correct. So we're basically, I know that I went through that slide quickly, but the difference between the beta units and the final units is that I think what everybody knows here probably in the quantum world is that it's one thing to be able to produce a product, it's another thing to be able to really nail it on stability. And Qunnect has been working hard to get all of the engineering elements correct on our instrumentation so that these things can start to be plug and play. And Mark 1 is really intended not only to perform slightly better than the Mark beta units, but significantly better on the stability and the engineering side.
Great, thank you, Noel. Chris and Steve, do you have any questions for Noel on that quantum memory?
Sure, this is Steve. One question would be, do you see people using it for something else besides a repeater? What other uses do you see?
This goes back to, there always will be academic customers. So I think the broad answer on that is yes for academic customers, because they may only want to use it also for the classical part of the memory and not necessarily the quantum aspect. But the other thing is that quantum memory really has sort of two functions, right? One could be literally just to serve as a data buffer timing element within a larger network. So, anytime you need to buffer the rate at which data is going from one point to the next, you could have a standalone quantum memory standing somewhere in the network. Or it could be as part of one of these larger multi-node systems that becomes a repeater.
Thank you.
Yeah, I have maybe more, I don't know if it's a question or a comment, but I could see kind of two directions for you to go into hardcore quantum computing this way. One, maybe harder, is to use the individual atoms. I think you have a vapor cell type model there. Yeah, to somehow get them to interact, maybe with Rydberg states and so forth. That's probably more academic. But maybe more interesting is the linear photonics version of quantum computers. They desperately need memory.
Yes.
Instead of circulating photons around and so forth. Do you look forward? I mean, if your system is a real commodity and you can just, it's just plug and play, like you say, I mean, I could see a real opportunity there. That's maybe more of a comment. I know you're going to agree.
No, of course, we appreciate that. So I can tell you that, so everything we do is vapor cells. So definitely the memory itself is a warm vapor cell, but then we also have our sources are vapor cells, our frequency locks are also vapor cells, but the sources also, in the way that you define them, right, can also be used in different configurations to be more like frequency converters, which you referred to earlier. And we certainly believe that one of the next major steps, both with our company and I think other companies that are starting to come online, is to look at how one is going to connect the quantum computers to the quantum networks, which absolutely are going to.
Excellent. Yes, I forgot to mention quantum transduction. That's
Well, that's coming up next, Steve. So go ahead and start it now.
Oh, okay.
Go
Well,
ahead.
yeah, so the networks are, well, the networks are useless if they can't connect to anything. So everybody's, trying to build towards telecom wavelengths and compatibility. But I think there's a wider use for transduction, as Chris was mentioning, and as you were mentioning. And I think your memories might potentially help with transduction, but is there any company or anybody looking at the transduction problem in a more general sense? That's it.
Loaded,
So I mean, there is a French company called QFox. Do I have the name correct? Who's starting to think about quantum modems. But I think what I was thinking more about is that the quantum memories themselves can act, depending on the configuration of them as frequency converters. We can also do things within that. It turns out that at this point, in order to get our basic products out there and into the world so people can actually test them and learn how to test drive them, we had to make a decision, which I think is true for Qubitekk and others on this call. I mean, as you're going through the risk part of what Mark was saying, and you have to put first products out, you have to make decisions. So ours right now is to be at our best operating wavelength, which is 795, but there's no reason that we have to stay there. Atoms have lots of lines, right? So we could operate at many of them. And certainly if you learn how to do things well within the memory, you could also be using them as versions of frequency converters or transducers.
Yeah, no, I can see that. But I'm wondering more about the general case of, can I connect anything to anything? And just being compatible on frequency or just, having the right line width. I may need other aspects to be compatible, not just one particular aspect. And what I would love to see is like a matrix of whose product can really interoperate with whose other product. So I can build products and know that they will interoperate with each other properly in all ways, not just on a particular wavelength and not work, in some other way. So I don't know.
So I think it's a great lead in to something that Mark had talked to us about as we were preparing for today's webinar. And that's what spec sheet is the dream spec sheet in terms of features that need to be out there for the entire community to be reporting in order to be able to make the judgment that you're talking about, Steve. So, what does everyone need to report? Because we all know that whenever we're publishing academic papers, I
put it up on the screen, Noel, actually. Go ahead.
So I think that one of the things which you had mentioned and we were just talking about is this idea of, should everybody be reporting brightness, line width, heralding efficiencies, et cetera? When you read the academic works which are out there, you'll notice that many of those, for obvious reasons, need to tune a lot of parameters simultaneously in order to get the best numbers, which end up being reported and published, right? But in order to actually get to the point where we have these as commercial instruments, we need to have whatever operating range that we're going to be producing, sort of as the spec sheet requires. So the last bullet, which Mark has posted here, this quantities that need to be defined, right? Whatever else is on the wish list there, that's something that we certainly should have open for discussion. But I think the idea of having brightness and line width being two major factors, which sometimes now are combined into a ratio called spectral line width, spectral efficiency, is something which would be very useful for everyone in the source community to start thinking about. And that plays into this idea of the compatibility. But I think reporting line width separately is something which is important, particularly in our field, but you're seeing it also in things like the paper that came out of the DeReed-Martin group.
This is excellent, yeah. And I would look at point to the QED-C standards. The QED-C QKD group looked at what kind of interoperability or characteristics are needed between components of a QKD system, and that would be the source detector and coincidence counters and all the other parts that might be needed. I think they've done some good work on trying to define that.
One of the other things that's occurring, as we alluded to, is that NIST is kind of getting into this and is going to start offering the ability to take sources and actually characterize them and produce standard data sheets, which is going to be, I think, huge for the marketplace in terms of interoperability, Steve.
Is there a particular person, Kay? I think there was some confusion when I had talked to others that if NIST was going to do that or not. Is there a particular person that's setting that up?
I do. I've been in contact with them. I can't remember their name right now, but I will get it for you in a few minutes, if I may.
Great. If you could post it in the chat, that would be great, Kay. Thank you.
I can do that. Yeah.
This is John Burke. Noel, for your quantum memory, is there like a metric like a read-write cycle error probability or something like that that can kind of define this quantum memory device? Do you have something like that? I'm sorry, I missed your presentation earlier. You already said this.
No worries. So, I mean, what we report as some of the basic sort of features of our memories routinely. Again, so I should say the list which is up there is the one we were thinking about for sources, right? So in the memory is something that we always think about is fidelity, which has a lot to do with how much all of our stuff is optical. So how much the qubit looks like what you put in, right? So that's directly in our case a function of the signal to noise, and the signal to noise on our beta units is around 95%, but we know we can get above that. It just requires some different optics that we're still fleshing out what that looks like in terms of putting it into a prototype. But right now, our signal to noise is around 15 and our fidelities are a little above 95%.
Okay, thank you. That helps a lot.
Yeah.
We're sort of a time check here. Thanks, John. We're at time here. We're going to continue. Anybody who wants to stick around, we're going to go for at least 15 more minutes. If there's still questions, I think the discussion is very interesting. I want to come back to, I think, Noel, I think Santanu had a question for you in the chat as well about the time of your memory. Maybe you can just type it in.
Thanks.
You want to comment on this, Chris?
Oh, I love that. I love that experiment. So what we have here are a couple of dilution refrigerators separated by about 20 feet, and they each have superconducting qubits in them, small chips, I guess. This is from ETH in Zurich. And what's connecting in there is what's equivalent to a microwave fiber. Single microwave photons, you can't deal with them at room temperature because room temperature has gazillions of them in the background. So this tube is cooled down to nearly absolute zero to allow single microwaves to go back and forth. But it's a version of actually the same type of thing we do in the optical domain. But you can see this is, their effective fibers are, a million times bigger. It's moving in the right direction. I think it's interesting. This is more of a researchy thing. But somebody mentioned transduction. I think there is a beautiful idea that's not ready for prime time. Certainly not ready for commercial activity at this time. But it involves superconducting qubits, which happen to have a natural frequency in the microwave domain, a few gigahertz. Now, if you make a microwave cavity and one of the parts of that cavity is on a mechanical oscillator, and then you send a laser beam of any color onto the back of that, you can transduce a qubit from the superconducting Josephson junction to the microwave to the optical photon, a single optical photon. Now, it's nowhere near 100% at any one of those stages. But there's beautiful work across the world in doing that. That to me is the most general transduction because it didn't matter what laser color you had there. The kind I work with, we have atoms that are very specific, also nulls. They have atoms that are very specific to a particular color. And there's some latitude there, but I think having a general transducer like that involves optomechanics is the buzzword. That's really cool. It's also a lot harder because it's so general. But so I don't know. My comments first is this is great research we're looking at here. And I think all these different quantum platforms are doing amazing things. They're starting to think about a modular approach.
Great. And then, Noel, I think we wanted to, let me see here. Yeah, Steve, you already hit that. So Noel, you want to talk about this? I think this is important, this concept. This is your material. So I just wanted to share it.
This is Noel's very busy slide, but something which I think is a great moment for us to reflect, right? So I put together this slide some time ago when I really wanted to think about the fact that the quantum internet is not going to be developed in 5 seconds because the digital internet wasn't either. So it was a nice reminder of the fact that it took 20 years to get all of the core pieces together in order to make the digital internet work. And those come in 3 flavors, which are color-coded as being blue, green, and purple. And it's the idea of combining hardware protocols and infrastructure. So some of the first hardware that came out for the digital internet was the stuff that came out of BBN in the 60s and Bell Labs as well. It took another 20 years to get us up to the point where TCP/IP became something that we all started using, and then of course years beyond that in order to get to the World Wide Web. So in quantum, what we're seeing is like the very first stuff, which is of course the basis of the very first QKD stuff that's out there, was the protocols described in '84. But as you keep pushing up, right, we've gone through many iterations now of expanding infrastructure and starting to build hardware. Of course, some of the first hardware coming out of Magic Q and IDQ. But as we're pushing into what are going to be the next sort of realizations of what the quantum internet looks like, I'm sure it's going to be some combination of learning how to interface the computers to the networks, or calling the networks miniature computers, depending on how you like to think about it. And that all of that will lead to what we might see as a quantum repeater in the next few years. But realistically speaking, when people start talking about the quantum internet, you're talking, I think, more than a few years into the future. So as a conservative estimate, but we should have patience because so many things were realized as we see the very early versions of what ARPANET looked like in the 70s, and we know what it is today.
You're muted, Mark.
Yeah.
Thank you. This is a really good slide from you as well. Care to comment?
Okay. So yeah, so for those of you out there who remember what a cray looks like, this is a nice little throwback to the fact that we know that without a network, massive quantum computers are basically doomed to operate in isolation. So that happened with the first iteration of of classical computers when we were thinking about things like the cray. And now we're starting to run into the same sort of problems if we don't think about what does it mean to actually network quantum computers. So there are a number of things that I've listed in the center there, which are types of technologies that were enabled by the networks, so the internet actually coming online. Of course, one of the earliest versions is the viruses, which is amusing. But as you keep going down, of course, there's a number of digital commerce things and other things, and social media, of course, that have been enabled over the years. But one of the very earliest examples of distributed computing, which I think we were all subject to potentially participating with, is SETI, the screensaver that was put out, by the Search for Extraterrestrial Life when they were looking to process the massive amount of data that they had gathered across everyone's computers, because everyone had the screensaver that was processing this stuff at night whenever they weren't actually using their processors for other things. But distributed computing is kind of the killer app right now of what I think we see as the potential of quantum networking. And again, the realization of what will come afterwards, I think we also just have to keep an open mind, because none of the things which you see in the middle column, we understood were going to be a realization as soon as the internet actually was built. So more to come, right? Exciting things ahead.
Yeah.
This is John Burke. A question. How do we envision a quantum internet when we don't really have an understanding of what a economically viable quantum computer, like a definition of what that is? I mean, in ARPANET, we had that, so there was an interface from which to connect, but I don't understand how we can even envision something now in the quantum domain.
So at the time, I'll take a first stab, but I welcome everyone to comment on
Yeah,
this. Right?
absolutely.
But I think the realization of, I mean, the early ARPANETs, we remember what the computer also looked like in those days, right? So it's not a terrible analogy to think of both still being very capital intensive problems right now. But what did exist at the time of ARPANET was a rather abundant copper wire network before things eventually went to fibers. Now we have all of the fibers out there who could potentially support the quantum internet. So the infrastructural piece exists, at least at the level of having the connections. Now we need to have the hardware. And in the early days of putting the BBN and Bell Labs hardware out there in order to start being able to do the packet switching protocols, they weren't cheap and they weren't plentiful. And I think that one of the criticisms of QKD on the front end, which the NSA had put out there, is the fact that we all know, upgrading this type of capital equipment in order to get better infrastructure is not going to be a cheap investment. So what are we willing to do for what type of pain points? And right now, there's sort of two sides to this. So as Steve mentioned, I think right now, what we know is an advantage is the cybersecurity advantage. So that's the pain point driving anything forward. So the first users of quantum internets or networks may be the government and defense customers, because that's where the pain point is today. And it's not going to be because you're going to have faster streaming or better data access. On the computational side, if we come to a point, it's always a balance between, can you build quantum processors that are larger, handling more qubits faster, and that sort of scaling, versus connecting lots of small quantum processors together, which are the arguments that Chris was making earlier about the scaling factors. So that would drive why you would want a quantum internet, even if it's at a very low scale, of being able to connect a lot of quantum processors together to realize a effectively larger processor for distributed computing. And please, other people comment.
Actually, I'd like to hop on as well, and I'd like to take this this slide a little step further. Let's go back to Morse code. Let's go back to the very first long distance, carrier wave transmissions. Let's go to the telegraph lines strung along the side of the railroad tracks. Let's go to people with switchboards. Everything starts with passing messages. And if we had never been passing messages a long time ago, we wouldn't be at the internet today. And really, in the 60s, no one, I'm pretty sure I bet some money on this, that no one could have foreseen where we are today when they said, oh yeah, let's connect these computers together. I mean, so we're, obviously we don't want to build it and see what happens, but there's a lot of us that are envisioning a great future, and if we never start pursuing the path, then we won't misstep and learn what the right path is. We'll be stuck learning these lessons later, and just to sound out some challenges. Other countries are pursuing these paths rapidly. And we need to learn the lessons, the hard lessons, whilst they do, or even in advance of them, rather than trailing.
Mark, can I make a little comment?
Go ahead, Sanu.
Actually, we heard a lot about transduction. And in my mind, ultimately, it's going to be the transduction efficiency. And all of these quantum computers, they are now like single module scale. And some of them are more amenable to higher transduction efficiency than others. So ultimately, combined with the basic computing hardware plus the transduction efficiency will probably determine the winners. Some systems like ion trap or optical, I think they're easier for transduction. But some of them with the RF-based qubits, they're really harder.
And you should also, just in general, I mean, this is something that I perhaps didn't emphasize enough at the beginning. We all know that when we try to connect two quantum anythings together, losses are really important. So it's not just going to be transduction, but you bring up a great point, Santanu. I mean, even just the coupling of the source to something can be significant enough that it's a problem.
I want to quickly address what John Burke mentioned, that it would be much easier to justify such a revolution of the infrastructure for quantum internet if we had a use case for quantum computing that is just super clear. And maybe it's not something as hard as factoring numbers, but something that you can do 10 million coherent ops on, I don't know, 5,000 qubits. Okay, I think those numbers are within reach. I don't know how many years. It'll be several years, but it's very hard to prove what you can do with those. It's probably going to be some kind of heuristics that are being used for optimization and so forth, which you can't really prove much about heuristics. It's just that they work. So I hate to say it's a little chicken and the egg. At that point, it'd be great if we had more milestones to go by to justify such an investment. But I think even to get to thousands of qubits and hundreds of millions of coherent ops, we're going to need a little mini internet, maybe not globally, but in one building or something.
Yeah, Chris, and this is Mark. I think that's what we're learning here in the laser prioritization tool with QED-C and the marketplace is that quantum computing has the funding to scale, and you and others that I've talked to are all saying, yeah, at some point we're going to need to use entanglement and these types of things to effectively, realistically scale quantum computers. Although all the quantum computing companies, when I talk to them, you're one of the ones that don't just beat this down my throat, which is it's all about qubits and quantum supremacy, right? But you can't just build everything on one processor, and that's not going to work. You're going to have to network it at some point. So if some of that funding comes from the quantum computing infrastructure, that would be great. That would address some of John's concerns, I think.
Question for Noel. Your
Yes.
system, how many dimensions of entanglement do you support? Is it by, is it a Bell state, or do you have n-way entanglement?
Yeah, so right now we're only handling polarization qubits, and we have a dual rail system which stores the horizontal and vertical polarization separately. So we split them, store them, then recombine them on the other side, one qubit at a time. So you have to start somewhere. So
the thing that drives that question is concern about scalability.
Yes.
Even in the QKD sense, we're stuck in this peer-to-peer world. And if Chris wants to do, every qubit talking to every other possible qubit in his system simultaneously, then, we need to work on scalability.
Yeah,
this
so
well, go ahead.
No, I was going to say, so multiplexing is possible. So we have plans already internally and some early data on how to multiplex these things.
Good.
And that's where it goes to. So the question is how to do that. But the other thing, which I think was on the back end of your question, is are you stuck with polarization qubits? I mean, we've been thinking a lot about how to transition to other types of qubits, which
that's transduction too. Yeah. Which
yes.
encoding are you using? Yes, exactly.
Yeah, which we think is also possible in our instruments. I mean, all of this stuff, it's, I think as you can appreciate, right, when you're trying to do the basic research and the product development at the same time, it's not fast. So we certainly, we have some things in the works, but they're not ready for prime time yet.
Sure. Okay, good.
And one thing I wanted to bring up, this is Hunter, a great discussion that we're having today. This is one of the best I've heard for a while. So one point I'd like to bring up that's non-technical, yet something we will need to consider as we're beginning to make these efforts more accessible to the general public, is the topic of quantum ethics. And since we don't really have a standards body for that, I think someone brought up earlier the point of interoperability, of making certain that when we are providing our benchmarks, that we are standardizing those. And perhaps this is a good time for us to talk about standardizing what our ethics are going to be in developing some of this technology. So I can already see some potential issues as we begin to integrate these systems with existing systems. So not to throw water on anything, but just more to bake in security from the beginning, because we all know security is a huge consideration and the topic of my entire career.
Great question. Who wants to take that one?
I'm sorry, I didn't quite, the question was about, and make sure we include security. And was there something about ethics?
Yes. And Mark, this is Hunter. My point was that I kind of went around the horn with it, bringing in some examples from earlier. But I think this is an opportunity for us as a group to build in and to standardize certain ethical considerations in the development of these technologies and talk about the standards we will build to as a group, especially since we're going to have so much influence on how this is built, implemented, and deployed worldwide. Have a unique opportunity to influence development in a positive way, preventing the future atom bomb in quantum form, basically.
So this is Kay, and that's a pretty profound topic, and I certainly can't comment on the ethics, but from a security and perspective, the work that we're doing at Qubitekk is, we always focus around having secure control of our devices, and there's currently it's kind of challenging if you think about how we as QKD vendors talk about, well, when quantum supremacy comes along and people can factor these numbers easily, then traditional PKI will fall down. So I hate to say it, we secure our devices with SSH using, TLS tunnels and stuff, but we will adapt and overcome in the future as better technologies come along. But we are using state-of-the-art networking protocols today, and when you hop on a network and communicate with one of our devices, you have to authenticate, and that's one of the things that we have. A lot of traction from some of our partners, where we're essentially protecting things like the energy grid, which are not necessarily specifically an atom bomb, but if someone can hack the energy grid and start making sympathetic superposition of load switching on and off at the wrong times, you can just bring down the grid and cause untold destruction, which is an atom bomb multiplied by a lot, because fixing the grid in the US would take 20 years if someone was to do a proper orchestrated attack. So I think these are some of the things that security that quantum can offer in the way of security, and certainly we do as vendors need to bake in security protocols from the start, and we need to be aware of the vulnerabilities that may exist in these protocols and keep updating things, just as with any network technology.
Most certainly. And Kay, I appreciate this response. It's fantastic. And I think you've hit upon a few other points in addition to what I was trying to bring out here. I think a part of my thought on this is premature given where we are in the development of the technology. However, I'm definitely a forward-thinking type person. And I think your list of protocols you follow, coupled with some of the other manufacturers here and folks who are part of QED-C, perhaps we could have a separate session. And I think I'll talk with Tom about this offline for setting up a separate thread where we can discuss quantum ethics and perhaps work together to create our own version of the Quantum Geneva Convention. These are the standards we will develop to ethically. And then over here, we have our technological standards development. But if we agree on how we'll move forward, we can make sure we solve many problems together, but we also prevent some, because I don't think we can foresee any of this. And is it Noel or Noel? I apologize, I don't know how to pronounce your name right.
So it's Noel, but I answer to both.
Yeah, thank you,
Yeah.
Noel. But what your point was on your first slide with the timeline was phenomenal. That was a great overview of how we can't even anticipate what will happen. And there were some other interesting developments throughout that timeline as well. Many of us were here for those. I know Tony Stieber and I were around for some of them, and I participated in that SETI initiative. So
Love it.
it's,
Great,
yep.
great, great.
Yes,
All
so
right.
I think I'll talk with Tom about this offline, but please put this in the back of your minds. I think we have a great opportunity to work on something amazing together.
Great, great. Thank you, Hunter. So I was gonna, I'm sure some people need to jump off. We have the upcoming schedule. So the next Quantum Marketplace webinar is gonna be on quantum timing in late September. Then we're looking to touch on fabrication services in October, electronics and RF in November, and then quantum test and measurement in January. And then, Chris, we're looking at coming into quantum computing and software and all of that after that. So let's talk about that as well. Celia, do you want to make a comment?
I do, thanks. And I appreciate those who were able to stick around. We've recorded this, so we'll make the whole thing, I think, available, certainly to the membership. And we can maybe summarize this in a little announcement that we put out so folks know they should come and listen to the whole conversation when they get the chance. I wanted to actually go back to Noel's timeline. And I can't resist actually putting in a plug for SRI, which didn't appear on it. But if you let me share.
Yeah, sure. Go ahead.
Sorry, Sylvia.
That's okay. So you can update it. And I will send you a link. I should put it in the chat or something to the mother of all demos that took place on December 9th, 1968. And Doug Engelbart of SRI demonstrated, as you can see down here on this YouTube, including shared screen teleconferencing at that time. So there was a connection between him in San Francisco and SRI down on the peninsula. And it was part of that original ARPANET demonstration in the late 68, early 69 timeframe. So SRI isn't all that visible as part of QED-C, but I think most of you know that SRI is the manager of QED-C, and SRI has a lot of a great track record and a strong history in this space. So I was pleased to see that reference and analogy. And while it's not perfect, of course, I think there are many that are worth considering. And yeah, we've come a long way since then. So thanks to everyone again. And this has been a fantastic quantum marketplace. We will continue to expand the publicity around these events, and I think we'll continue to have a growing audience for them. Hopefully, they'll prove valuable to the folks who were able to join, especially the providers of technology. And things are happening quickly, so I think we'll have to revisit this in a year or less and see what's happening. So thank you all.